And we're recording now. Okay, so we're almost done, folks. Check our schedule here. Down to our last two sections, 16.8, give you a quiz today, then 16.9 Tuesday. Now, if I have the time, and I think I do, I'm actually going to sneak in some of 16.9 today, at least show you one problem with it. I especially want to show you the real long one, okay? It will help you for today's quiz, because today's quiz will be just like that. I showed you one last time that would be like today's quiz, and there's another one in 16.9 that's kind of like that. And besides, I wanted to at least show you something from 16.9, so then you have at least a week to see how it works, as opposed to waiting until Tuesday to show it to you. Then you only have 2 days for it, okay? So goal is finish 16.8, sneak in at least one long problem with 16.9, maybe more. Okay, and otherwise I'll finish it on Tuesday. Then Tuesday, as soon as we're finished, you can ask questions. We'll have a question and answer session at the end. And then Thursday, you have the entire class period once again for the exam. Then Tuesday the 18th, just a question and answer, or more like a review for the final exam. So you say, how do I study for the final exam? Just look back at all the old exams. And I'm leaning towards something like giving you maybe 15 questions. 3 from each test. So I'll pick 3 from the first test, 3 from the second, 3 from the third, and so on. I'm not promising you the same questions, but they might be, or similar. As far as cheat sheets are concerned, you can just bring all the previous formula sheets. No reason reinventing the wheel. If you already got your formula sheet from the first test, and then the second test, right? And the third test, fourth test, and well, we haven't had the 5th test yet, but we're getting that. Just bring all those formula sheets in, okay? I hope you still have them. But if you don't have them, you lost it or you threw it away, you can make another one. Okay. And by the way, you're allowed to add to it. So maybe during the test, you said, oh yeah, I wish I put that down on my cheat sheet. You can do it now. You can add to it when it comes to the final exam. Okay. So say for the final exam, ground rules, you can have 5 formula sheets. How's that? Okay. And the easiest is whatever you use for the first test and whatever you use for the second test, third test, fourth test, and 5th test. Okay. And then we'll be done with the course, 2 weeks from today? Is that right? Today's the 6th. So yeah, 2 weeks from today, we're finished with the class. How's that? Okay. All right, so I'll do 16.8, sneak in a little bit of 16.9, and then we'll have our quiz. Okay, and let's see. Question. Let's see. Okay, so yeah, if you just joined, go ahead and put that. We had 10. Okay, I see something in the chat. So yeah, there will be about 15 questions. That's what I'm leaning toward for the final. Okay, and theoretically, it's something you can finish within 2 hours and 15 minutes. I'll try to make sure that that's the case. Well, when I give you the problems. Okay. All right. Any other general questions about the test? And anybody who joined late, go ahead and put your name in. Jerry, I got you. Well, I'll get you later. I put away my row sheet. I don't like to take it out once I put it away. Okay, so we'll get started. Okay, so 16.8 is on Stoke's theorem. Okay, and again, the one theorem, one formula for that. Page 1134. It's higher dimensional form of Green's theorem. Green's theorem was in a plane. Stoke's theorem is in 3 dimensions. You could integrate along a boundary curve. That's called the integral of f dot dr. And by the way, that's the same thing as work. So if it asks for work, that's the left side, integral of f dot dr. It's kind of useful because work in physics, some of you know physics, work is force times distance. So this could be thought of as force times a little change in distance. Okay, so maybe I'll put down here work. So it asks for the work done, integral along the curve of f dot dr, or double integral of curl of f dot ds. Now curl of f is also a vector, which means all the formulas that we had before for vector dot ds also hold for curl f dot ds, and I'll show you when that shows up. Okay, so we had some of that in the previous section. Okay, now it turns out for the problems that they give us, sometimes the left-hand side is easier. Sometimes the right-hand side is easier. Okay. The language from the problems that they give you tells you what to do. And I'll use similar language for the exam and also the final exam. Okay, exam is cumulative. Yes, because I'm picking problems from every exam, so it's obviously cumulative for the final exam. Okay, so there's no hard and fast rule as to which is easier, the left side or the right side, but you can tell from the language that they use. So that's the ground rules that I would have you follow. Okay, so what are you talking about? Okay, I already did number one, same boundary curve, right? Okay, look at the language for problems 2 through 6. It says use Stoke's theorem to evaluate the double integral along the surface of curl f dot ds. Okay. Because they're using that language, it means don't do what it says, do the other side. Okay, so in other words, for 2 through 6, if it says use Stoke's theorem, don't actually do what it says. In this case, do the left-hand side. In other words, do the left integral of f dot dr. It's easier. See the language? And then after that, there's some problems that says use Stoke's theorem to evaluate the integral of f dot dr. It means do the right-hand side, double integral of curl f dot ds. Right? Okay, so highlight this. So we'll write 2 through 6, use Stoke's theorem to do blah, blah, blah. It means do the integral along the curve of f dot dr. That says do there, do. And then for 7 through 10, use Stoke's theorem to evaluate the integral of f dot dr. It means do this. So do double integral along the region S of curl f dot ds. See that? Because I want you to recognize that when it comes to the test also, because it's easier. So if it's easier, they're telling you, okay, don't actually evaluate along the curve, do the other. So when it says use the theorem to evaluate blah, 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 it means do the other side. So that means for 2 through 6, do f dot dr. And then if it says use Stoke's theorem to evaluate f dot dr, it means do curl f dot ds. Okay. All right, so here we go. So number 5. So capital F of XYZ is XYZI plus XYJ plus X squared YZK. S consists of the top and the 4 sides, but not the bottom of the cube with vertices plus or minus 1, plus or minus 1, plus or minus 1, oriented outward. Okay. So here's the picture. So here's the cube. We've seen that already. Plus or minus 1, plus or minus 1, but there's no bottom. So the boundary curve, it's not really a curve, it's a square. It's z equals -1, correct? Z equals -1. So I decided to break it up into 4 pieces. It's a lot of work, yes. Do the 4 pieces. So 1, 2, 3, and 4. This is in the XY plane. It's really not in the XY plane. It's the XY plane down 1 unit because z is -1. Okay, so C, the curve, is made up of C1 plus C2 plus C3 plus C4. Okay, you say, how do you know where to start? It doesn't matter, but as long as you're going in a positive orientation is considered counterclockwise. Now, in the direction it said oriented outward, if you take the shape, outward would be up, and up is considered positive, right? Okay, now let's make things easier on ourselves. Okay, I'm evaluating the bottom boundary curve. We will say curve, but it's a square. Z is -1 everywhere on the curve. So I plug in -1 here and -1 here. I now have -xy, xy, and -x² y because Z is -1 along the boundary bottom. Okay, put -1 there, -1 there. So that's my new F. Okay, fortunately, just think of the XY plane down 1 unit. Okay, so C1, Y is -1, X goes from -1 to 1. Okay, so now I plug in there. If Y is -1, put a -1 there, and I have X. Put a -1 there, I have -X. Put a -1, let's see there. Okay, X². Oh no, not really happy with that. That should be a positive X², but fortunately, it works because the dot product is good. Yeah. If I plug in -1, it should be X². I'm sorry, that should still be -1. Position vector. Okay, position vector is X, Y, Z. I messed up here and I messed up here, but it actually doesn't matter, as you'll see in a second. Okay, so the position vector is X, Y, Z. Okay, X is X, Y is -1, and Z is -1. That's right. If I'm along here, which means DR is 1, 0, 0. It's basically I, which is very nice. So even though I messed up here, it was going to turn out to be 0. And if I messed up here, it still comes out to be 0. So DR is 1, 0, 0. So now I do F dot DR. So F dot DR, the dot product, X times 1 is X, -X times 0 is 0, and that times 0 is 0. So fortunately, even though I messed up here, it ends up being 0. So F dot DR is X. So that's what I integrate. So the integral along C1, I'm going as X goes from -1 to 1 of X dx. That's X²/2 from -1 to 1. That's 1/2 minus 1/2, 0. Okay, so you can see how long some of these are. And yes, I'll keep that in mind when I construct the test and the final exam. Okay, C2, X equals 1. Y goes from -1 to 1. Okay, so I plug in X equals 1. If I put X equals 1 here, that becomes -Y. Plug in X equals 1 here, I get Y. Plug in X equals 1 here, -Y. Because I'm plugging in X equals 1. What is the position vector? X, Y, Z. Well, X is 1, Y is Y, Z is -1. So DR is 0, 1, 0. Oh, I messed up again. Should be 0, 1, 0, but I got the correct dot product. I think I was going too fast maybe. So what's the derivative of this? 0, 1, 0. So now I dot F with DR. So -Y times 0 is nothing. Y times 1 is Y. -Y times 0 is 0. So Y. And that's what I'm integrating. Okay, so integral along C2 of -1 to 1 of F dot DR. F dot DR came out to be Y dy. Y²/2 from -1 to 1. That's also 0. Okay, now C3 is a little bit tricky. I have to go this way. So if I have to go that way, when I integrate, it's from 1 to -1. Okay, this is Y equals 1. X goes from 1 to -1. Okay, remember, I'm oriented, I'm traveling in this direction. So I have to go from 1 to -1 right here. Okay, so Y equals 1. So look back here. Where to go? Plug in y equals 1. Negative x. Plug in y equals 1. X. Y equals 1. Negative x squared. And off to the side here, I put y equals 1. What's r? X, y, z, but y is 1. Z is always negative 1 for this problem. So dr, the derivative is 1, 0, 0. Perfect. So what's f dot dr? Let's see. So negative x times 1 plus nothing, negative x. So I want the integral from 1 to negative 1 of negative x dx. So that's negative x squared over 2 from 1 to negative 1. But again, both of these are going to be negative 1/2. So negative 1/2 minus a negative 1/2. So that's also 0. Okay, finally C4. C4, x equals negative 1. And again, we're going down. So y has to go from 1 to negative 1. Okay, so y goes from 1 to negative 1. Okay, so plug in x equals negative 1. Put negative 1 there, and I have positive y. Put negative 1 there, negative y. Put negative 1, let's see, where is it? Where am I? Yeah, put negative 1 there. Negative 1 squared is 1, so I have negative y. So I'm plugging in x equals negative 1. What is the position vector? X, y, z. Well, x is negative 1. Z is negative 1, and y is still y, of course. Okay, so what's dr? Derivative 0, 1, 0. So take the dot product, f dot dr. Y times nothing is nothing. Negative y times 1 is negative y. Negative y times 0 is 0, so negative y. Okay. So you can see some of these problems are really long. I know. Okay, so C4, integral from 1 to negative 1 of negative y dy, that's also going to be 0. As you can see, so negative y squared over 2 from negative 1 to 1. Again, you get negative 1/2 minus negative 1/2, which is 0. Okay, so along all 4 of them, you get 0. So the integral around the entire curve, which is a square, is whatever I got for C1 plus C2 plus C3 plus C4, which is 0 plus 0 plus 0 plus 0, and the answer is 0. Okay, I guess you could say all of that for nothing per se, but all of that comes out to be 0. Okay, so we had to evaluate along each of these 4. Okay, so yeah, if you were thinking that assignment was short, it looks short, but sometimes the problem can get really, really long. Okay, so that was 5. I'll leave you to do 3 on your own. Okay, next one I was going to show you is 7. Again, look at the language. Use Stoke's theorem to evaluate the integral of f dot dr. That means do curl of f dot ds. Okay, so capital F of x, y, z is x plus y squared I, y plus z squared j, z plus x squared k. C is a triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So this is what we got. The equation of the plane is x plus y plus z equals 1. Okay. If you want to get that fast, okay, normally you would go ax plus by plus cz equals, I'll write it, equals the least common multiple of 1, 1, and 1, which is 1. And then you would just plug in. If you plug in 1, 0, 0, you get a as 1. Plug in 0, 1, 0, b is 1. Plug in 0, 0, 1, c is 1. So you get x plus y plus z equals 1. So that's the equation of this plane that goes through that covers that triangle. Easy to check. Plug in 1, 0, 0, it works. 0, 1, 0 works, 0, 0, 1 works. Okay, so I need curl F. How do I do curl? I, J, K is always the top. The middle is always partial with respect to X, Y, and Z. And then X plus Y squared, Y plus Z squared, Z plus X squared. Okay, so the I component is that, nothing, minus that, negative 2Z. The J component is the opposite of that, 2X, minus that, which is nothing. And the K component is that, nothing, minus 2Y. So I have negative 2Z, negative 2X, negative 2Y. Okay, you might recall to find DS. Curl F dot DS. I can take the dot product of curl F dot N D non-vector S, non-bold S. Okay, so I need the normal vector. Well, normal vector is 1, 1, 1, but it needs to be unit normal. So unit normal is 1, 1, 1 divided by square root of 1 squared plus 1 squared plus 1 squared, radical 3. Okay. So curl F dot N. So negative 2Z times 1 over radical 3 minus 2X times 1 over radical 3 minus 2Y over 1 radical. They all have a negative 2. They all have a radical 3. It'll be X plus Y plus Z. Okay. So double integral over the region S. The region S is this triangle. Factor out the negative 2 over radical 3. Integral of X plus Y plus Z ds. Okay. And then in the XY plane, looking over here. So in XY plane, just think of going 0, 1 to 1, 0, right? That equation is Y equals 1 minus X. I'm integrating X plus Y plus Z. But X plus Y plus Z is 1. So I'm just integrating 1. That's nice. And then ds, I multiply by the Jacobian dA. So X plus Y plus Z equals 1. Solve for Z. Z is 1 minus X minus Y, right? So I have negative 2 over radical 3, square root of 1 plus Z sub X squared. Partial with respect to X is negative 1. Squared, you get 1. Plus partial with respect to Y, negative 1. Squared, 1. So negative 2 over radical 3 times radical 3 times dA. dA is the area in the XY plane. The area right down here in the XY plane is 1/2. 1/2 base times height, 1/2 1 times 1 is 1/2. Okay, so final answer is negative 1. Okay, so this is 1 plus Z sub X squared plus Z sub Y squared right over here. Okay, so that's everything there. So let me go back and show you all of that again of how that one worked. Okay. Okay, I think I threw out number 9. Yeah, I didn't do 9. So you don't have to pay attention right now. I'll just show you how I started it. 9 looks like this. Okay, it got too long. So they gave me this, they gave me this. So I did the curl. That came out nice, negative Y, negative Z, negative X. Okay. They told me Z is 1 minus X squared minus Y squared. Z sub X was negative 2X. Z sub Y was negative 2Y. But then when I try to do curl of F dot ds, which is negative P Z sub X minus Q Z sub Y plus R dA by formula, it came out to be way too long. Okay, so I decided to just forget about it. Okay, all right. Now, 13 says verify that Stokes' theorem is true. I'm not going to have you do that because it's too long. What does it mean to verify Stokes' theorem is true? That means you're supposed to do both sides. You're supposed to do the left side. You're also supposed to do the right side. Okay, that's too long. So I decided to change it for you. So here's my new directions. For 13, only do the integral of f dot dr. For 15, only do integral of f dot dr. It's easier. And 17, we're also going to do f dot dr. Okay, and actually for 17, it says find the work done. 17 at the bottom there, find the work done. That by definition means do the f dot dr one, integral along the curve of f dot dr. Okay, so you see how this one is actually not so bad at all. If you only do f dot dr part. Okay, so capital F of x, y, z is negative y, x, and negative 2. Let me show you that. 13, capital F of x, y, z, negative y, x, negative 2. S is the cone, z squared equals x squared plus y squared, z between 0 and 4, oriented downward. Oriented downward means negative, because positive is up. All right, so what I decided to do, z goes from 0 to 4. So if I plug in 0, right, you're at the origin. If you plug in 4, z squared is 16. So I have x squared plus y squared equals 16. Well, switch to polar coordinates. X is 4 cosine theta, y is 4 sine theta, and z is 4. Right? So it's a downward facing curve. All right, so now the f becomes negative y. So negative y is negative 4 sine theta. X, which is 4 cosine theta, and then negative 2. Then I want f dot dr. Okay, so I need r prime. R prime is the same as dr. Maybe if that helps. F dot dr, or think of it as derivative of r. So derivative of that is negative 4 sine theta. Derivative of that is 4 cosine theta. Derivative of 4 is 0. Okay, and now I take the dot product. That times that, 16 sine squared theta. That times that, 16 cosine squared theta. That times that is 0. So I have 16 sine squared theta plus 16 cosine squared theta, factor out to 16, and you have sine squared theta plus cosine squared theta, which is 1. So I'm integrating 16. Very nice. Okay, so if I go around the boundary curve, all I have left for the integral of f dot dr is negative. Okay, negative because of downward orientation, it said. Negative integral from 0 to 2 pi, because we're going all the way around a circle, of f dot dr, 16 d theta. This is a constant. These are constant. So negative 16 times the length of the interval, 2 pi, negative 32 pi. So that actually was not so bad at all, as you can see. Okay, then 15. Do also. Okay, capital F of X, Y, Z is Y, I, Z, J, X, K. S is the hemisphere, X squared plus Y squared plus Z squared equals 1, Y greater than or equal to 0, oriented in the direction of the positive Y axis. Okay. All right, X squared plus Y squared plus Z squared equals 1. That's a sphere. Y is greater than or equal to 0. Okay, and it says the positive Y-axis going this way. Now, if you only have this part, you're going inward, right? Can you see this hemisphere? Okay, there's a hemisphere. If I didn't have this restriction, I got the whole sphere. Now, Y is greater than or equal to 0, so you throw out this part. Okay, so you have this part here. The boundary curve is basically X squared plus Z squared equals 1 and Y equals 0. Inward is negative because it says in the direction of the positive Y-axis. Okay. Remember, for a closed curve, outward is considered positive. I'm going in. Okay. So if you have this part of the sphere, if I go this direction, I'm going inside, so it's going to be negative. All right. So the boundary curve is X squared plus Z squared equals 1 with Y equal to 0. Once again, switch to polar coordinates. So R is a position vector. X is cosine theta, Y is 0, Z is sine theta. I know you're used to X and Y, but here it's X and Z. In the XZ plane, X is R cosine theta, but R is 1. It used to be Y, now it's Z is R sine theta, but R is 1. So cosine theta, 0, sine theta. And now what is F? Okay, F is Y, Z, X. Y is 0. Z is sine theta. X is cosine theta. That's my new F. dr is the same as r prime. So I differentiate these guys. Derivative cosine theta is negative sine theta. Derivative 0 is 0. Derivative sine theta is cosine theta. And then I take the dot product of F and dr. So 0 times anything is 0. Sine theta times 0 is 0. Cosine theta times cosine theta, cosine squared theta. So I'm integrating cosine squared theta. And that should do it. All right. So integral along the curve of F dot dr is again negative because it's inward. Inward is negative. From 0 to 2 pi of cosine squared theta d theta. And remember how to integrate cosine squared from Calc 2? Change it to 1 plus cosine 2 theta over 2. Remember that? Okay, so I factored out the half. So negative a half. Integral of 1 d theta is theta. Integral of cosine 2 theta is sine of 2 theta times a half from 0 to 2 pi. So you plug in 0, you get 0, right? 0 there, sine of 0, 0. Plug in 2 pi plus 1/2 sine of 4 pi. Sine of 4 pi going around twice, that's 0. So negative 1/2 times 2 pi. Final answer is negative pi. Okay. All right, so I think we're good there. One more I want to show you was 17, but that's another one that's very long. Okay, let me do my focusing thing real quickly here again. Okay, so again, language, the language that I would put on the test, okay, if it says, you can even put this in your cheat sheet if you want. If it says use Stoke's theorem, okay, so remember Stoke's theorem is that the left side is equal to the right side. integral of f dot dr is a double integral of curl f ds. If the language is use Stokes' theorem to evaluate the integral of curl f ds, it means do the integral of f dot dr, use the other side. And likewise, if the language is use Stokes' theorem to evaluate the integral of f dot dr, it means do the double integral of curl f dot ds. Okay, so let me quickly do my focus thing again. And right here, I don't know why it switches to yellow color. And there's that. Okay, and you don't need number 9 because that's a skip. There's 13.
Professor, real quick.
Yeah, let me show this real quickly first.
Okay.
And get this out of the way. Okay, yes, question.
For number 13, right there next to F, what is that? That little right to the right of F.
This one here?
No, up there, 4 negative 4 sine theta, 4 cosine. What is that? There.
NEG, negative?
No, not right next to, is that R, vector R, right there, negative 4 sine theta, 4 cosine theta, 0?
Oh, yeah, right here.
Yeah.
Yeah, that's R prime.
Oh, R prime.
And that's an arrow indicating it's the same as DR. Sorry
Okay.
about that.
R prime.
R prime is the same as DR.
Okay.
Actually, it looks better here. So DR, when it says F dot DR, DR is the same as R prime. In fact, and way I would remember is derivative of R, right? DR. Tiny change in R prime.
Okay.
Is that what you mean?
Yes.
Okay. All right, good. Okay, anything else, please? Questions? Okay, then I just have one more problem to show you, 17, but that's going to be a while. So I might start it and then we'll break. And then after the break, yeah, I actually would have finished 16.8, but I'm going to sneak in some of 16.9, especially the real long one, and it'll help you for the quiz today too, which might be long. It's one of those where you have to analyze the 6 surfaces. Okay, so 17. Our particle moves along line segments from the origin, 0, 0, 0, to 1, 0, 0, to 1, 2, 1, to 0, 2, 1, and back to the origin in space. Under the influence of the force field, capital F of x, y, z is z squared I plus 2x, y, j plus 4y squared k. Find the work done. So work is the integral of f dot dr. So we are indeed doing this. Okay, so they say start at the origin, go to 1, 0, 0. So that's L1, L2, go from 1, 0, 0 to 1, 2, 1. Then L3, go from 1, 2, 1 to 0, 2, 1. And then L4, 0, 2, 1 back to the origin. Okay, so I have to analyze L1, L2, L3, and L4 in this order. So you go from 0, 0, 0 to 1, 0, 0 to 1, 2, 1 to 0, 2, 1 and back to the origin. Okay. Now, mind you, for most of these problems, you do not have a conservative vector field. It's too easy. If it was a conservative vector field, the answer is 0, right? You have a closed path, but it's not true here. So I have to find the integral along the curve of f dot dr is, I'm going to have to figure out what I get for C1, C2, C3, and C4 and add them all up. All right, so here are the curves from 0, 0, 0 to 1, 0, 0. Okay. Well, y is stuck at 0, z is stuck at 0, x is equal to t, and t goes from 0 to 1. L2, X is constantly 1, right? So I'm really thinking of going from 0, 0 to 2, 1 in the Y, Z plane, so to speak. Okay. Now Y is going twice as fast as Z. So that leads me to believe Y equals 2t, Z equals t. T goes from 0 to 1. Okay, L2, I'm going from 1, 0, 0, 1, 2, 1 to 0, 2, 1. Y is constantly 2. Z is constantly 1. X goes from 1 to 0, and I have to be careful about that. Okay. Or I could say X equals 1 minus T, Y equals 2, Z equals 1. T goes from 0 to 1. Okay. So if you stop and think about this, if you plug in 0, you get 1. And if you plug in 1, you get 0. So X is 1 minus T, Y is 2, Z is 1. I'm just describing the curves right now. Alternatively, remember a while back, you had a way of going in a line segment from one point to another, right? So if you go from R0 to R1, there was a formula for that, right? It was 1 minus T R0 plus T R1. So you could do that. Okay. We had that a while back. It's going to take me a while to find it, but it's there. But I don't think it's that hard to convince you, this works. Then finally for L4, okay, from 0 to 1 back to 0, 0, 0, X is constantly 0. Once again, Y is twice as big as Z. Okay, so X equals 0, Y equals 2 minus 2T, Z is 1 minus T, T goes from 0 to 1. Okay. I'll go ahead and sneak it in here, I think, again. It was this formula. If I get my pen to work. R of T is 1 minus T R0 plus T R1. Remember that one? To determine a line segment from one point to another. So you could use that for each of these. Okay, and a double check. If I plug in 0, I'm at 0, 2, 1. Correct. And when I plug in 1, I'm at 0, 0, 0. Okay. So I've described the 4 line segments. Here's L1, L2, L3, and L4. Okay, so we'll break until our usual roughly 7:10-ish. Okay, so at 7:10, I'll finish this problem and then sneak in a little bit of the divergence theorem, and then we'll take our final quiz of the semester. Okay, so take our break. Anybody who joined late, please put your name in the chat and I'll get you later. Okay. Okay, folks, we'll pick up where we left off. Okay, let's see. Elliot, I got you for attendance. So you're good. Jerry, I got you for attendance. And I think that's that. All right, so let's pick up where we were. So I don't think I have to go much longer. Okay, so I'm going to finish up 17. I'll do one problem from 16.9, but it's a real long one. And it'll help you for the quiz. It's similar to the quiz. Okay, the quiz is actually sort of like the last one I did last time also. Okay, so I think there was 29. Okay, so just before the break, this is where I left off. I got an expression for L1, L2, L3, and L4. Okay, now for F, I'm going to plug in. F very conveniently is 0, because if I plug in z squared, z is 0, 2xy, y is 0, 4y squared is 0. Okay, I did r prime, although it doesn't matter. If I dot it with F, it's going to be 0. So remember, this is r. R is t 0, 0. So r prime is 1, 0, 0. Anyway, f dot dr is 0. So I'm integrating along C1, f dot dr is the integral of 0 dt, which is 0. Okay, L2, I established this. And now F plugging in, right? So I plug in z squared is t squared. 2xy, 2xy is 4t. And then 4y squared, 4y squared, 4 times 2t quantity squared, 4 times 4t squared, 16t squared. And then dr is the same as r prime. Remember, this is r. Okay, x, y, z is r. So the vector can be thought of as 1, 2t, t. All right, so the derivative is 0, 2, 1. Take the dot product. Okay, t squared times 0 is 0. 4t times 2 is 8t. 16t squared times 1 is 16t squared. So t is going from 0 to 1. I set this up so that all of them t are going from 0 to 1. So I take the integral of f dot dr, which is 8t, that's an 8 there, sorry. 8t plus 16t squared dt. Integral of 8t is 4t squared plus 16t cubed over 3. Plug in 0, you get 0. Plug in 1, it's 4 plus 16 thirds, 28 over 3. Okay, L3. So I established this before the break. So what is r prime or dr? Derivative of this is -1. Derivative of that is 0. Derivative of that is 0. So r prime is -1, 0, 0. Okay, so F is z squared. Z is 1, so I have 1. I'm plugging in. And then let's see. Let's see, where am I? Now, how did I get this? 16 times see what I did here. It's -1. Four times x times y. So 1 minus t times this. In actuality, it doesn't matter what these are because I'm going to multiply by 0 and 0 anyway. Okay, and I have 16. 16 times 1 is 16. Okay, but in reality, you don't really care what these are. It's 1 something something dot -1 0 0. So maybe I'll just leave it like that. Forget what these are. But it's what you get when you plug in theory. But 1 times -1 is -1. And then whatever times 0 is 0, and whatever times 0 is 0. Okay, so if you don't understand what happened here, okay, which I'm kind of questioning myself, it doesn't really matter because when you multiply by 0, it's 0. So F dot dr is -1. Okay. 2x y. I plugged back in 2 times x times y. 2 times, I see 2 times 2 times 1 minus t. And then, yeah, okay, I get it now. 4y squared. That's where I got the 16 from when I plugged in. Anyway, it comes out to be -1. So integral from 0 to 1 of -1 dt. And that's -1. Okay, it's a constant, so it's -1 times the length of the interval, which is 1. Okay, and finally L4. So F is plugging in z squared. Z squared is 1 minus t squared. 2xy, but x is 0, so that's nice, so that's 0. And then 4y squared, 4 times 2 minus 2t squared. And now r prime. So derivative of this is 0, -2, -1. Okay, so for the dot product, let's see, that times that is 0. The middle component times that is 0. That's also nice. So the only thing of substance is -1 times 4, 2 minus 2t squared. So -4 times 2 minus 2t squared. So that's what I'm integrating. All right, so integral from 0 to 1 of -4, 2 minus 2t squared. Take out the -4. I'll do the power rule combined with the chain rule. So I did 2 minus 2t cubed divided by 3. And then by the chain rule, if I differentiate, I'd multiply by -2. So when I integrate, I divide by -2. Right? You could also do a U substitution. I think it's faster if you do it this way. From 0 to 1. Okay, this time when you plug in 1, you get 0. Not when you plug in 0. Right? 2 minus 2t. So I plug in 0, I have, let's see, -4 over -6 is 2/3. You have 2 cubed, which is 8. So I have a -8. 2/3 times 0 minus 8, -16/3. So finally, I got them all. So the integral along the first curve was 0. Second one was 28 over 3. Third one was, where'd it go? -1. And the fourth one was -16 over 3. So at long last, integral along the curve of f dot dr is the sum of all of them. Just add these 4 numbers up. So 0 plus 28 over 3 minus 1 minus 16 over 3, 3. Okay. It's long, I realize that. So it's not likely I would have you do this entire kind of problem on the test, unless it's something that's easy enough and fast enough that can be done in a short amount of time. Okay, so, I have to keep that in mind when I construct the test. And you keep that in mind too, as I construct the test. So if you're probably saying to yourself, he's probably not going to give me anything that long, you're more than likely correct. Okay. All right, so I'm done with that. Let me do my focusing thing, and then I'm done with the section. And we're down to one last section of Calc 3. How do you like that? But again, there's one problem that's so long that I decided to show it to you tonight rather than be in time trouble next time. I'll show it to you today, and there still should be plenty of time for you to do the quiz, I hope. Okay. All right, so that is that. 16.8. Last topic of Calc 3, 16.9, the divergence theorem. Page 1141. Here it is. Let E be a simple solid region, and let S be the boundary surface of E with positive outward orientation, positive is outward, and let capital F, bold F, be a vector field whose component functions have continuous partial derivatives on an open region that contains E. Usually you don't have to worry about that. Then double integral along the surface, it's a closed surface now, of F dot ds is a triple integral of the region E of the divergence of F dv. Okay, and the picture on page 1147, I showed you this last time. This is what's happening. Okay, so in that picture, that last picture in red, almost always it's easier to do the triple integral. It sounds counterintuitive, but for a picture like that, you would normally do 6 double integrals, right? The front, the back, the left, the right, the top, and the bottom. For a case of a box, it's even worse when you have pictures that are not a box. But let's just say you have a box. So do you want to do 6 double integrals or 1 triple integral? It's normally easier to do 1 triple integral. Okay, so double integral along the surface F dot ds equals a triple integral of the 3-dimensional region E of the divergence of F dv. Okay. And now for the one problem that's really long, and since it's not even quite 7:30, I'll go ahead and do the one. Okay, so number 1, verify the divergence theorem is true for the vector field. Okay, verify means actually do both sides. And that's the only one I'm going to have you do. Okay, so all the others, like number 3, we're supposed to do both of them. We're only going to do the easier one, the triple integral. So for number 3, just do triple integral. And then after that, see where it says use a divergence theorem to calculate the surface integral. Same language. It really means do the triple integral. It becomes easier for all the rest of them. Okay, so I'll just do number 1, and this kind of runs parallel with your quiz. In fact, your quiz is going to be much easier than this. Okay, so f of xyz is 3xi plus xyj plus 2xek. E is the cube bounded by x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, z equals 1. Okay. So here we go. So here's a divergence theorem. We know how to compute a divergence, right? That was back in section 5, I believe it was. All right. So my capital F of xyz is 3x, xy, 2xz. This is P, Q, and R. The region E, they said was 0, 1 cross 0, 1 cross 0, 1. Okay. So what's the difference between S and E? S is only the surface. So the 6 surfaces of the cube, as opposed to the whole cube, including the inside. You're integrating along the whole inside. Okay, now look at the easy part. The easy part is a triple integral. Divergence of F. So divergence, you might recall, is the partial of P with respect to X, P sub X, plus the partial of Q with respect to Y, plus the partial of R with respect to Z. So derivative with respect to X is 3. Derivative with respect to Y is X. Derivative with respect to Z is 2X. Add them up, 3X plus 3. So if you triple integral 0 to 1, 0 to 1, and 0 to 1, 3x plus 3 dz, dy, dx. These are all constants, does not depend on z. Take out the length of the interval, 1. Does not depend on y. Take out the length of the interval, 1. So I'm just integrating from 0 to 1 of 3x plus 3 dx. Very nice. 3x squared over 2 plus 3x from 0 to 1. Plug in 0, you get 0. Plug in 1, you have 3 halves plus 3, 9 over 2. Now for the no fun part. Integrate the 6 faces, and you'll have to do this on the quiz also. So double integral along the surface. Well, the 6 surfaces are x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, z equals 1. Then I have to do f dot ds. Okay, and recall f dot ds, I'll write it here. Double integral of f dot ds is the double integral of f dot n d scalar s, vector s, ds, vector, f dot n, the normal vector, ds, which is surface. Okay, in this case, all the surfaces are 1 by 1 or 1. Okay, x equals 0. Okay. Well, f is, if I plug in x equals 0, 0, 0, 0. Nice. So f dot ds is 0. Okay, just so you know, the normal vector is negative I. Okay, for the back, where'd it go? X equals 0, that's the back. Positive is outward, so the outward vector is negative I. Okay, x equals 1, the front. The unit normal vector is positive I, right? For the front surface, you're coming out. Okay, so f is 3y2z plugging in. How did I plug in? Okay, so I plugged in x equals 1, 3y2z. N is I. So double integral f dot ds, double integral of f dot n ds. So f was 3y2z dot the normal vector 1, 0, 0. Dot product is 3 times 1 plus nothing plus nothing. So the integral of 3 ds, which is 3. Double integral of ds is just the area. Area of each of these is 1. They're all 1 by 1. Whoops, where'd it go? Right? They're all 1 by 1. The one we had last time, they were all 2 by 2, right? Because it was going from -1 to 1 for x, y, and z. Okay, so I did the front and the back. Now the left and the right. Y equals 0. The left face. So for the left face, what's the unit positive vector, meaning outward? Going to the left, so it's -j. And then f becomes 3x, 0, 2xz. How do I get that? I plugged in y as 0. So y equals 0, that's 0. So 3x, 0, 2xz. Okay, so f dot ds, f dot n ds, you'll be doing exactly this on today's quiz. So 3x, 0, 2xz dot 0, -1, 0. So 3x times nothing, 0 times -1 is nothing, 2xz times nothing is nothing, double integral of 0, 0. Okay, so far I've got 0 going out toward the back, 3 units going out the front, 0 going out the left. And yeah, you can think of this as flow of anything, flow of water, flow of heat, flow of electricity. Okay, then y equals 1. Right surface. What's the unit normal vector going out? J. So, whoops, n is j. Plug in y equals 1, 3x, x, 2xz. So plug in y equals 1 here, 3x, x, 2xz. So f dot ds for the surface y equals 1, double integral y equals 1, f dot n ds. So f is now 3x x 2x z dot 0, 1, 0. 0 times that is 0. 0 times that is 0. So I just have 1 times x, which is x. So double integral from 0 to 1, 0 to 1 of x dx dz. Okay, the surface is the right surface, right? So x goes from 0 to 1, z goes from 0 to 1. And let's see, this does not depend on z. Take out the length of the interval, which is 1. And integral of x is x squared over 2. Plug in 1, you get a half. So half a unit is going out the right surface, I guess is the way you say that. Okay, then I have top and bottom. Oops. Bottom is z equals 0. Z equals 0. Plug in, I now have 3x, xy, and 0. Let's see why. Plug in z equals 0. That's nothing. These stay the same, right? So I have 3x, xy, and 0. That's my updated f function. By plugging in, the unit normal vector outward is negative k for the bottom, right? Think of the floor. Your floor unit vector outward is down. So negative k. All right, so f dot ds along z equals 0, f dot n ds. So 3x, xy, 0 dot negative k, which is 0, 0, negative 1. 0 times 3x is 0, plus 0 times xy, 0, plus negative 1 times 0 is 0, integral of 0, 0. So nothing's going out the bottom. 5 down, 1 to go. And then I'm finished for the day. Okay. Yeah, it's almost bordering on torture, I suppose. But so that's why I would not most likely not have you do something like this on the exam, but I don't mind doing it on a quiz where you can collaborate and you still have almost what 50 minutes or something as soon as I'm finished blabbing. Okay, top z equals 1. Top unit normal is k, right? So plugging in 3x, xy, 2x. How do I get that? I plug in z as 1. That stays the same. That stays the same. 2x times 1 is 2x. And unit normal is k. So double integral at z equals 1 f dot ds. Double integral z equals 0 f dot n ds. So it's 3x comma xy comma 2x dot k, which is 0, 0, 1. So 3x times nothing plus xy times nothing plus 2x times 1, which is 2x. So double integral of 2x dx dy. This does not depend on y. Take out the length of the interval 1. Integral of 2x is x squared. From 0 to 1, I get 1. So think of it as 1 unit going out the top. And I finally got them all. So the back has no net flow. The front has a net 3 units out. Y equals this. So the left, nothing. The right, half a unit outward. Remember, negative would be inward. And then let's see, the bottom, nothing's going out. The top is 1. So I add them all up. So the double integral along S, f dot ds, 0 plus 3 plus 0 plus a half plus 0 plus 1, 4.5 or 9 halves, which is the same answer as I got over here. But look at how much easier this one triple integral was compared to doing all of this stuff. Okay. And so for most of the rest of the problems in this section, we will just focus on the right-hand side. It's much, much easier. Okay, and we'll do, so I did problem 1 already. And so next time, Tuesday, I'll finish up 16.9 and then I'll leave it to questions and answers. If you have a question and answer session as usual, just before the test on Thursday, then we'll bring that up. Okay, so let me do the focus job. Take your questions if you have any, and if not, we will go straight to the quiz. Okay, I guess I have to scan back and forth here. I know what I'll do. I'll go do each letter. X equals 0. I'll go across. So x equals 0 was the back. X equals 1 is the front. Okay, then y equals 0 would be the left. Okay, y equals 1 is the right face. And then z equals 0 is the bottom. And then z equals 1 is the top. And those 6 double integrals came out to be 0, 3, 0, 1/2, 0, and 1. Add them all up, 9/2. And this was way easier, as you can see. All right. Okay, I'm done, folks. So we still have almost 45 minutes to do that one problem. Whoops. Let's see. What would the S vector be here? So ds. Okay, so I stopped sharing. Let me made a mistake there. So f dot ds is a tiny change in a vector across the surface. So think of this piece of paper, okay, and heat is going through it. Okay, so that would be a vector. Okay, so f dot d vector s is, it could be thought of as work, force times distance. Okay, so if you have a force, it depends on what direction you have, right? And depending on how you come through the surface. So if it comes through the surface at an angle, right, it's not going to be as strong as if I go straight down. Okay, or equivalently, you're going to have f dot n unit normal vector times the scalar ds, which is a tiny change in the surface area. Okay, so that's what's happening in that case. All right, anything else? Chat. All right, quiz time. So be ready to take a picture or do a screenshot. Let me get the quiz, and that'll be it for today. Okay, so next time I'll finish up again 16.9. And then if you have any questions in preparation for the test from chapter 16, you can bring it up next time. Here we go. Evaluate the flux of F across the surface S. S is the surface of the cube, 0, 1, cross 0, 1, cross 0, 1. It's kind of the one we just did. X is 0, X is 1, Y is 0, Y is 1, Z is 0, 0 is 1. Capital F is 2xi plus 5yj plus 6zk. Similar 16.7.29. Now, do not do this problem with the divergence theorem that I just showed you. You weren't supposed to know it yet. Okay, work it out by actually computing, all 6 surfaces, add them all up and go from there. Okay. All right, I'll hold it for maybe 10 more seconds. I'll assume everybody would have it after that. Evaluate the flux of F across the surface S. So your 6 surfaces are x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, z equals 1. Capital F is 2xi plus 5yj plus 6zk. And it's very similar to 16.729. Okay, I'll assume everybody has it now. So go ahead and get started. I'll set up your breakout rooms. Stop the share and get set up here.